Okay, we're going to take a look at another example of a proof by contradiction. This time we're going to use irrational numbers. And even though irrational numbers are not the ones that we're going to be typically working with, we do want to make sure that we are thinking about this as thoroughly and as carefully as we can, that all things are taken into account. So, again, a proof by contradiction. So we're going to start that by making an assumption of the opposite here. So we are saying that square root of 5 is irrational. So our assumption is that the square root of 5 is a rational number. Now, what does that mean? This means there exists two integers, p and q, that are relatively prime, which is another way to say that they have no common factors, such that the square root of 5 is equal to p over q. Okay, so that's our assumption, that if square root of 5 is rational, then there's two integers that we can divide and we will get the square root of 5. Okay. So the way we're going to deal with this, the first thing we're going to do is we're going to get rid of the square root over the 5. Okay, how do we typically do that in math and algebra? We square both sides. So squaring the square root of 5 will give us 5, and then the other side we get p squared over q squared. Okay, do a little bit of algebra here. We can multiply both sides by q squared, and I get 5q squared equals p squared. So now we have 5 times a number equals p squared, which is another way of saying that p squared is divisible by 5. So the way we write that is we would say 5 divides p squared. But 5 is a prime number. So what's good about that is that means that we know that 5 actually divides p. Okay, because it's a prime number, we know that that will work out. So what happens if I know that 5 divides p, then I also know, so let's go some arrows there. So we also know then that 5 squared must also divide p squared. But remember, we said that p squared, if we come back up to this statement right here, p squared is equal to 5q squared. Okay, so p squared is equal to 5q squared, which means that we can say that based on this, that 5 squared, so this is going to give us, so we know that p squared equals 5q squared, which means that 5 squared divides 5q squared. So there must be some integer k such that 5 squared times k equals 5q squared. Okay, so let me say that again. So we're saying that since 5 squared divides p squared, and we know that p squared is equal to 5q squared, we know that it also divides 5q squared. So there's some integer k that allows us to say that. But the next step, if you notice, is that I'm going to go ahead and divide both sides by 5 here, and I get that 5k equals q squared. But going back to what we said earlier, so we are basically saying that 5 times a number equals q squared, which means that 5 divides q squared. And like our previous argument, that also means then, because 5 is a prime number, that 5 must divide q. And this becomes our contradiction. Because if you remember, we said that if the square root of 5 is rational, p and q must be relatively prime. They have nothing in common. But we've just shown that if we make that assumption, then both p and q are divisible by 5, and they're not relatively prime. So there's a contradiction with our statement. So another way we can show this is if we have kind of two arrows going at each other like this. Okay, so there's our contradiction. So therefore, the square root of 5 is irrational. And this can be done certainly with any square root of any prime number, it's easy to follow the same steps in order to do this. Okay, we'll put our little box in to say that we're done, and there you go.